A tunnel is dug along the diameter of the earth. There is a particle of mass m at the center of the tunnel. The minimum velocity given to the particle so that it just reaches the surface of the earth is, so capital R and capital M denote the radius and mass of the earth. And the options are root gm by r, root gm by 2r, root 2gm by r, and 0. So let's see which one of them is the correct one. Now there is a particle which is initially at rest at the center of the earth, and we are supposed to give it a minimum velocity such that it just reaches the surface of the earth. So when it reaches the surface, its velocity should go to 0. So for this problem, we can consider the center as our initial state, and when it just reaches the surface, that will be our final state. Okay, and since the particle is moving in a gravitational field which is always conservative, we can use conservation of energy and write initial kinetic energy plus initial potential energy must be equal to final kinetic energy plus final potential energy due to conservation of mechanical energy, since the particle is moving in a conservative field. Right? So all we need to know is how to find the potential energies. For this, you need to know two important expressions as far as Earth is concerned, which is a solid sphere assumed to have a uniform density throughout its volume. Right? So what is the potential of a solid sphere at the surface? At the surface, it is minus gm by capital R, where capital R is its radius. And potential of a solid sphere, that is Earth in this particular case, at the center is minus 3gm by 2r. You should remember these two expressions. So now let us substitute for the conservation of energy equation. What is initial kinetic energy? Well, that is half mass of the object which is being projected with a minimum velocity that we are trying to find out. So it will be half mv minimum square. Potential energy is mass times potential at the center, which is minus 3gm by 2r. So that's why it becomes negative, is equal to final kinetic energy. It should just reach the surface according to the problem. So at the surface, its velocity should be 0. So kinetic energy will be 0. So what is the potential energy? Well, it is again m times the potential at the surface, because the particle is at the surface now, which is minus gm by r. Agreed? So let us solve for it. So half m v minimum square is equal to 3gm m by 2r minus gmm by r. Right? You can see mass of the particle cancels out. So the minimum velocity has got nothing to do with the mass of the particle. It is independent of it. And I'll have v minimum square by 2 is equal to gm by r is common, 3 by 2 minus 1, which is half. So it will be gm by 2r. 2 gets cancelled. So the minimum velocity turns out to be root of gm by r. This is the velocity to be given to the particle at the center of the earth, such that it just reaches the surface of the earth. That's the required answer. V minimum is root of gm by r. And which is the answer that supports us? Yes, it is option A. A tunnel is dug along a diameter of the earth. If ME and RE are the mass and radius of the earth respectively, then the force on a particle of mass m placed inside the tunnel at a distance r from the center is, and assume the walls of the tunnel to be frictionless. And here are the options. So please go through it, and which is the right answer is what we have to find out. So let us begin. So what we have here is a particle which is inside a tunnel dug along the diameter of the earth, and the center of the earth is at a distance r from the position of the particle. We need to know as to what is the force acting on that particle. Well, we know that Earth attracts all the particles towards its center. So obviously the force on this particle is directed towards the center of the Earth. The particle has a mass m, and we need the magnitude of that force. So we know that force is nothing but mass times the gravitational field of the Earth at the position of the particle, and we know that the particle is inside Earth, so we are interested in the gravitational field due to Earth at a point inside. So at this point, we will assume Earth to be a solid sphere having uniform density throughout its volume, which is a decent assumption. And for a solid sphere having uniform density, the gravitational field inside at any point is given by g mass of the sphere by radius cube of the sphere into distance from its center, of course in magnitude. Okay, so that's what we need here. So we have force F is equal to m into g mass of Earth divided by radius of Earth cube into distance of the particle from the center of the Earth, and from the diagram it is very clearly what? R, right? Small r. So rewriting it, we have the force is equal to g mass of Earth, mass of the particle, into distance of the particle from the center divided by cube of the radius of the Earth. That is the required answer for this particular question. It is g small m mass of Earth into r, the distance, divided by cube of the radius of the Earth. That's the required answer. And which is the option that supports us? Yes, it is option A. Suppose a vertical tunnel is dug along the diameter of the Earth, assumed to be a sphere of uniform mass density rho. If a body of mass m is thrown in this tunnel, then its acceleration at a distance y from the center is given by, and the options are 4 pi by 3 g rho ym, option B 1 by 4 pi rho gy, option C 4 by 3 pi rho y, and option D 4 by 3 pi g rho y. Which is the correct answer? Let us see. So we have a particle which is thrown along a tunnel dug along the diameter of the Earth, and at some instant of time it is at a distance y from the center of the Earth, and we need to find its acceleration at that point in terms of capital G, right? Universal gravitational constant and density of the Earth, and of course the distance y from the center. If at all, it depends on one of them or all of them or any two of them. Let's see which one is the right one. Correct? Now, at this instant, when it's at a distance y from the center of the Earth, obviously it is getting attracted towards the center with a force F, and the gravitational force on that F can be written as mass of the object in question times the gravitational field of the Earth at that point, and that point is a point inside Earth, so we are looking at E inside. And what is the expression for the gravitational field inside? It is minus g mass of Earth divided by radius cube into distance from the center. In this case it is y. So let's write down. First, force can be written as mass into acceleration. So m into a is equal to, of course there's a minus, g m by r cube into y. Correct? First thing, we can cancel off the mass of the particle in question, so it is independent of that. Now a is minus gm by r cube into y. We have got the answer, but then we want it in terms of density. For that reason, we can write mass of Earth as density times its volume. So which is 4 pi by 3 r cube. Correct? Now from this, m by r cube can be written as 4 pi rho by 3. Of course, such a definition is true only for a solid sphere whose density is uniform throughout its volume, and the problem expects us to assume the exact same thing. So we can apply this discussion or this result to this particular problem, right? So now come back to A. A is minus G into M by R cube, which can be written as 4 pi rho by 3 into Y. And finally, you have A is equal to minus 4 pi rho G Y by 3. That is the answer. Of course, minus sign is only indicating that acceleration and the distance from the center or the displacement from the center of Earth are oppositely directed. The problem is asking only for the magnitude of that acceleration, which is 4 by 3 pi rho Gy. That's the required answer. The acceleration is 4 by 3 pi rho Gy. And which is the option that agrees with this result? Yes, it is option D. Suppose a smooth tunnel is dug along a straight line joining 2 points on the surface of the Earth, and a particle is dropped from rest at its one end. Assuming that the mass of Earth is uniformly distributed over its volume, then the options are: the particle will emerge from the other end with a velocity root gme by 2 re, where me and re are the mass and radius of the Earth respectively. Option B, the particle will come to rest at the center of the tunnel. Option C, the potential energy of the particle will always be equal to 0 at the center of the tunnel. And option D, acceleration of the particle will be proportional to the distance from the midpoint of the tunnel. So let's see which one of them is the right answer. Let's move ahead to the solution. So here is Earth. A tunnel is dug at its center along its diameter, and there is a particle which is released from rest at one of its ends. And obviously, the gravitational field of Earth is always pointing towards its center. So the particle is accelerated towards its center. And at a given point of time, let us say the particle is at a distance x from the center of the Earth. Right? Now, by the courtesy of a theorem in gravitation, if a particle, or if at a point inside a solid sphere, a particle exists, it experiences a force only due to the mass of the sphere inside that particle. The force due to the mass which is outside that particular sphere is 0. So now if I ask as to what is the force on this mass when it is at a distance x from the center of the Earth, it is mass times the gravitational field due to Earth at a point inside. And what is the expression for the field at a point inside? It is minus gm by radius of the Earth cube into distance from the center, which is x. Clear? So substituting that, we get force is equal to mass into minus gm by r cube into x. Agreed? So what is force according to Newton's second law? We can write it as mass into acceleration. Of course, the mass we are concerned is the mass of the particle, which is m into a is equal to minus m into g capital M by r cube into x. You can see that m gets cancelled, or we have a is equal to minus gm by r cube. In that, I can take gm by r square outside, and gm by r squared is nothing but the acceleration due to gravity at the surface of the Earth by r. 1r remains, isn't it, into x, where we have used the fact that g is equal to gm by r square at the surface of the Earth, correct? So now it is very, very clear that the acceleration is directly proportional to displacement and oppositely directed. Displacement from where? Displacement from the center of the Earth. Now this is a clear case of simple harmonic motion. So since we have released the particle at rest from one end, That becomes the extreme point because it is starting from rest. Velocity is equal to 0 at extreme point in a simple harmonic motion, isn't it? So what will it do? It will go till the other extreme, which is the other end, stop, come back to the center, right? Go to the other end, and it will continue to oscillate along that tunnel, along the diameter of the earth. And what is the amplitude of oscillation in this particular problem? Well, it is the mean position is the center, correct? Extreme position is at the end point. So the amplitude is nothing but the radius of the earth. So it will oscillate. It will oscillate 100%. And one of the options says potential energy is 0 at the center, which is wrong. Earth to be considered as a solid sphere of uniform density throughout, potential at the center is the maximum. If potential is maximum, potential energy is mass times potential, so that is also the maximum, right? In magnitude. In magnitude. Of course, there's a minus sign along with it. Agreed? So this is what is happening, guys. So the potential energy will not be 0. It will be mass times the potential at the center, and potential at the center is 100%, not 0. And it will not come out of the other end because it will stop at the other end and start moving back towards the center, right? So acceleration is directly proportional to the distance from the center. Yes, agreed. And it will be SHM. So that is the information we have to capture, and that is what will help us in finding out the correct option. So let's have a look at the options once again. So option A is wrong because it will not come out of the other point. It will come to rest there and it will again come back to the center. Particle will come to rest at the center of the tunnel. No, the velocity of the particle will be maximum at the center of the tunnel because that corresponds to the mean position of SHM. Agreed? And option C, potential energy of the particle will always be equal to 0 at the center. Wrong, it won't be. It will be non-zero. And option D, acceleration of the particle will be proportional to the distance from the midpoint of the tunnel. Yes, because the midpoint of the tunnel coincides with the center of the earth. Yes, it is true. We have proved it. So option D is the correct answer for this particular question. If a tunnel is cut at any orientation through the center of the earth, then find the time taken by a ball released from one end to reach the other end, that is the diametrically opposite end. Neglect Earth's rotation and take radius of Earth as 64 into 10 to the power 5 meter and acceleration due to gravity at the surface of the Earth to be 10 meter per second square. The options are 84.6 minute, option B 41.9 minute, option C 8 minute, and option D depends on the orientation. So let us see how to solve this. So what is done here is that tunnel is dug along the diameter of the earth and a ball or a particle, whatever it is released. That means from rest, it is released at one end. So obviously earth is attracting all particles towards the center and it will accelerate towards the center, and once it crosses the center of the earth, earth is still pulling it towards its center, so it will start decelerating. Of course, let's say it reaches the other end. What is the time it takes to do so? That is what we have to answer. So in order to solve this, I'm going to assume a general state of the particle when the particle is at some point inside the earth at a distance of x from the center of the earth, right? So it will have some velocity at this point. I'm not interested in. We are interested in as to what is the force it experiences at this general point we have considered. What is the force? Well, the force is mass times the gravitational field of the earth at a point inside, right? Why? The particle is inside, obviously, isn't it? So what is the gravitational field inside a solid sphere having uniform density throughout its volume is what we are assuming earth to be here. So that will be minus g mass of that solid sphere divided by cube of its radius times the distance from the center. the distance from the center of the point in question. So let's substitute. So the force here is mass into minus g into mass of earth divided by radius of earth cube into the distance from the center in the position we have considered as x, which you can see in the diagram, right? So force according to Newton's second law can be written as mass into acceleration. So I'll have mass into acceleration is minus g capital M small m by r cube into x. Small m gets cancelled, or A becomes minus gm by r cube. And from gm by r cube, if I consider gm by r square taken outside, that is nothing but acceleration due to gravity of earth at its surface. So this becomes g by r, isn't it, into x. So the moment you arrive at this particular expression, things should light up in your brain. What? Well, it is nothing but A is equal to minus omega square x form, which implies this particle is executing SHM inside this tunnel. This particle is executing SHM inside the tunnel, correct? And what is omega of that SHM? Well, it is g by r under root, because omega square is g by r upon direct comparison between the two equations. Yes or no? Right? So the particle is executing SHM and omega is root of g by r. If I go for the time period, it is 2 pi by omega. So which is 2 pi root of r by g. So we have got the time period of this SHM, which is 2 pi root of r by g, where r is the radius of the earth and g is the acceleration due to gravity. Agreed? Now what is asked for? What is the time it takes for the particle to go from one end from which it is released from rest to the other end? So since it is executing SHM, as I told you, when it goes to the other side, it will start decelerating. So if it starts from rest, that means it is starting from an extreme position in SHM, and symmetry dictates that the other extreme position will be the diametrically opposite end, isn't it? So this will also be an extreme position for which it will come to rest again because it is executing SHM. So what is the time taken to move from one extreme position to the other extreme position in SHM? Well, it is nothing but half the time period, isn't it? T by 2 is what we are looking for. Half the time period. We know what the time period is. We want T by 2. So let us start. So we have got T is equal to 2 pi root of r by g. 2 pi is 6.28 into root of r. 64 into 10 to the power 5. This is what the problem asks us to consider r as, divided by g, which is 10 according to the problem. So I'll get 64 into 10 to the power 4 under root. So it simplifies as 8 into 10 to the power 2. 8 into 6.28 turns out to be 50.24 into 10 to the power 2 becomes 5024 seconds. 5024 seconds, right? And what we want is T by 2. Our answer is T by 2, isn't it? So T by 2 will turn out to be 2, correct? 5, 1, 2 second. Now divided by 60, you will get the answer close to 41.9, and of course it becomes in minute. So the time taken for the particle to go from one end to the diametrically opposite end, since it executes SHM, is T by 2, and that T by 2 turns out to be 41.9 minutes, and that is the required answer, and which is the option that agrees to this result? Yes, it is option B.